We are on Chapter 4, Discrete Random Variables. This is where the fun stuff really begins. So, 4 sections to look at. Basically, I'm going to show you what the 2 types of random variables are. So we'll learn about discrete and continuous. We'll expand on these concepts as we keep going throughout the course. We're going to look at discrete probability distributions, which are sort of the easy versions of the ones that come after, which are the continuous probability distributions. And those are the ones where we're going to bring back those z-scores. So that'll be fun. That's coming up in the future. The binomial distribution. Big topic that we're going to use a lot, and we'll see it in this context and also in a z-score context later. And then just a little topic, something called the Poisson Distribution. That one is, well, we'll talk about it when we get there. Topic that I need to show you, but not going to test you on very thoroughly at all. Okay, what is a random variable? So a random variable assumes numerical values that are determined by the outcomes of an experiment. So let's fill that in. Perfect. There are 2 types. There's discrete and continuous. So what's a discrete random variable? Well, those are basically integer values, so possible values that can be counted or listed. So integers like 1, 2, 3, 4. Practical examples might be like the number of something being sold in a week, so like Ipods. The number of times my cat pukes on the carpet in a month, 1, 2, 3, 4, right? So they're discrete because they can't puke 1.5 times on my carpet. They can only puke once or twice or 3 or 4 times. Or the number of stars you rate your Uber driver. Okay, let's compare that with the continuous random variable. So these can assume any numerical value in 1 or more intervals. There are an infinite amount of values, so we'll fill in that word infinite. So there are an infinite amount of values that the variable may take. These are like real numbers. And when I say real numbers, I'm talking about the real number system. So what that basically means is, if you look at the examples, you can have any decimal on those. So, for example, the amount of time that you wait in line at the grocery store could be a continuous random variable because you might wait for 1.54 minutes. It might be 5.89. Depending on how precise your watch is, you could go to 9.459 minutes. So they're continuous because you can have many different values on an interval. The height of a randomly selected person is a continuous random variable because, again, you can have decimals in there, right? So people aren't necessarily 187 centimeters tall. They might be 187.23. Or the weight of an average household trash or something like that, okay? So there you have it. Get those definitions out of the way. What is a discrete probability distribution? Well, the probability distribution of a discrete random variable, either in a table, graph, or a formula that gives the probability associated with each possible value that the variable can assume. The notation you guys are going to be familiar with from the probability unit we did. We usually denote values of the random variable by using the letter x, and the values associated probability by writing p of x. Remember, that's how you pronounce it. That's p of x. You write a p, and then the variable in the brackets after. Couple properties that are going to be important. So for any value x of the random variable, p of x has to be greater than or equal to 0. That goes back to that concept we talked about in probability where probability of something has to be 0 or higher and has to also be less than 100%. So that's actually connected to the second point. Whereas if you take your table and you have all your associated probabilities, if you add them all up, they must sum to exactly 1. So again, you'll see this notation here again. It's the sum of every p of x equals 1. And I'll show you with an example very shortly, like right now. So here we have a table of discrete random variables. Now I know they're discrete because it's the number of iPods sold, right? So I can't sell like 1.5 iPods, right? So I can either sell 0, 1, 2, 3, 4, or 5. Then we have the associated probability in the next column here. So the probability, the way I would read this is the probability of selling 0 iPods is 0.3 or 0.03 or 3 out of 100. Probability of selling 1 iPod is 0.2. Probability of selling 2 is 0.5. Okay? So we're going to be using this to do a couple calculations in a moment. There's a couple other bullets you can read through here. It's just defining like what X is, that X is the number of iPods sold per week. And it's just saying that it collected the data over 100 weeks. So let me show you a formula maybe before we actually do a question. So what is the expected value of a discrete random variable? Well, in previous weeks we talked about the mean, X bar, or if it was population, we'd say mu. The mean or expected value of a discrete random variable is defined as such. So this looks pretty complicated, but let me break it down for you. It's this just means the sum. And by now you guys should be fairly used to this. We see this symbol all the time nowadays in our course. So it's the sum of every x times its associated probability. We write this as mu of x. So that's how you pronounce that, is mu of x. And it's just, you see the x is just a little subscript down there. And mu is the value expected to occur in the long run and on average. So just a fancy way to say, hey, here's how we calculate the average when we have one of these discrete probability tables, okay? So let's take that table from before. So here's that number of iPods sold table again. And we're just gonna ask the question, how many iPods should be expected to be sold in a week? So I'm just reminding you here that here's your little formula. I'm obviously not gonna do that on an assignment, but I will remind you that I've created a formula sheet and I update it week to week as we go along so it doesn't get too overwhelming. And over here, you're gonna see the heading discrete random variables, and you'll see the formulas that we'll be covering today. So that's pretty handy. So make sure you're familiar with what the formula sheet looks like, and keep it with you, put it on your fridge, keep it with you at all times. So let's calculate that expected value for the number of iPods sold. So this formula says I'm going to do the sum of every x times its associated probability. So looking at my table, I'm going to start with the first one, which is 0. So I'm going to go 0 times p of 0 plus, right, because it says the sum, and then I'm going to go 1 times probability of 1 plus 2 times probability of 2, and so on and so forth. So I'm just writing this just so you kind of know what's going on until I get to 5 here, okay? So I made a little mistake there, just ignore that. 5 times probability of 5. So I'm just saving some time. I'm going ... just saying I'm going to do 3 and 4 in there. Now I'm actually going to show my work on the next step. So I'm actually going to take the probability of selling 0 iPods and multiply it by its associated probability, which is 0.03. Now I need to do the same thing for 1, so I'm going to go 1 times probability of 1, grab it from the table, it's 0.2, and then plus 2 times probability of selling 2 iPods, which is just 0.5, plus probability of selling 3 iPods, so it's 3 times 0.2, plus 4 times, look up the probability of 4, so that's 0.05, and then plus 5 times 0.02. So this is what I'd be expecting for work. Advantages of showing me this is I can see if you make any mistakes and just deduct a very small amount of points if you happen to make a mistake. And I suggest you pause the video at this point, plug this into your calculator, and see if you get the same answer as me. So when you do that, you're gonna get 2.1. So this is 2.1 iPods sold per week. Sold per week. There we go. And now I left a little blank here so you can write it out. Perfect. Okay, so that's how you use the formula to find the expected value. So just watch out for that. It's a pretty typical question. You see the expected value, I might say, what's the average or something like that. Lots of different ways to ask it, but it is just going to be this formula if it's a discrete probability distribution. All right. It wouldn't be fun if we didn't talk about variance and standard deviation. So that means you're going to have 2 more formulas here to look at. So the variance of a discrete random variable is as follows. Now remember, we don't often use variance in actual real life. Usually we do the square root of it to get the standard deviation. So just like before in the other week there, the standard deviation is just the square root of the variance. If you are going to calculate the standard deviation though, you're likely going to be using this formula here. So let's just step through it. It's kind of a big one. So you have the sum, and now it's every x minus the mean squared, and then times the associated probability. Okay, so you take every x, you subtract the mean. We just calculated this in the last example. So this you have to calculate, or it'll be given in the question. So calculate or given. Okay, so usually these are like multi-step questions, like part A, I'll ask you to calculate the mean, and then in part B, I might ask you what's the standard deviation or something like that. So we'll do an example of this right away, so you can see what it looks like. And I'm just gonna bring up the formula sheet, and I'm gonna point out that for a discrete random variable distribution, here is the standard deviation or the variance. Remember, the only difference between these two formulas is that the standard deviation has a big square root over the whole thing, right? So you calculate your variance and then you do the square root at the end and you got your standard deviation. I have both formulas on there, but there you have it. So same example as before with the iPod sold. So what I've done is I sort of summarized the table over here for you guys just to make your notes nice and easy and straightforward. So there's the table, same numbers as last time. I also have the variance formula up here for convenience. Calculate the variance standard deviation of the number of iPods sold at Best Buy in a week. I'm just reminding you that from the last example, we calculated the expected value or the mean at 2.1. Why? Because we need it in the formula right there, right? So I have sort of the sample calculation started out for you guys because it is your notes. I want it to be organized. So let me break this down for you. So I recommend you start at the top of the table. So I'm taking x, which is 0, plugging it in here, and then it's subtracted the mean, 2.1, and then all of that is squared. And then the formula says times p of x. So the p of x for p of 0 is 0.03. So there it is right there. Let's see if you can get the next one. So I'm now doing x is 1. So I plug in 1, subtract the mean, 2.1. I'm going to square the whole thing, so put brackets around it. And then times the associated probability. So this is p of 1, right? If you look at the table, there it is, 0.2. Okay? So on and so forth. So if you look at x equal 2, so I go 2 minus 2.21, square that whole thing, and then the associated value for probability of 2 iPods sold is 0.5, so it's just multiplied right there. Then I did the good old plus ... and you go on. So I will actually write it out. So just down here, I left you some room, and you can try it out yourself, and then either pause the video and check, or just try to follow along with me, whatever you prefer. So I got 3 minus 2.1, times, now probability of 3 is 0.2. So there it is. Plus, now I'm going to go 4 minus 2.1 squared. And then probability of 4 is 0.05 plus, let's see, 5 minus 2.1 squared times probability of 5 is 0.02. Okay, a couple of things that you might not remember from math class from before. You do the brackets first. Okay, so when I'm calculating this, for example, I'm going to be doing this first. So I'd be going 1 minus 2.1. That would give me negative 1.1. And then it's squared. So you'll never get a negative number in here. You know, on your calculator, I'd recommend that you do this. Go 1.1, square it, hit equals, and then just multiply by 0.02. Now you can either write down all those individual numbers. I recommend you do that, or you can keep them in your calculator. Some people are comfortable doing that. The key here is going to be doing the homeworks, right? Which I have detailed solutions for that I've developed, and you're going to want to just make sure that you get used to either plugging it all in on your calculator and then showing me this work on the page, or just writing down each one. Okay, you're going to have to experiment for what strategy works best for you. I personally like to sort of write out each one. So on the next step here, I left some room for that. So if you type the first one in on your calculator and just rounding to sort of 4 decimals, you don't need to keep every single decimal. We'll talk a little bit more about rounding later, but not right now. So that's what you should get for the first one. So try the second one, pause the video, see if you can get it. So for that one, I get 2.42 plus, try the third one here, plug it in on your calculator and see if you get this. And I'm just going to keep writing, and you can certainly pause the video and just try it out. All right, congratulations if you made it that far. You are a star. And now see if you can add them all up. So I get 0.89. So this is the variance. That was something they're asking for, so I'll put a box around that. There we go. And you'll notice that the notation for variance has a squared in it, right? Because it is the standard deviation squared, so you see it in the notation. All you need to do to get the standard deviation is take this number and do the square root of it. So down here, I kind of got you started out by reminding you that the standard deviation is the square root of the variance. I'm going to pop it in there, so try that out on your calculator. And when you are done, you'll get 0.94. Yay! Right, pat yourself on the back for that one. That was a long example. Not very easy, so it is key to, do the homeworks. Try this example out again later. That's usually where I like to start, is by rewriting my notes. Next major topic here is the binomial distribution. It is my favorite distribution, and you might see it referred to as the Bernoulli process after the dude who figured it out. So this is a distribution that describes data concerning situations where only one of two things can happen. So you'll have to watch out for it in questions, but basically watch out for things that are like yes-no decisions, correct or incorrect answers, defective, not defective, like parts, voting, not voting. Anything that is a dichotomy where there's only two possible outcomes is going to be a binomial distribution question. There are 4 characteristics of this sort of experiment. Basically, look for these things in the question. Experiment consists of n identical trials. Like, for example, you're asking the same question to 50 different people, and maybe it's like a yes-no answer. Each trial either results in success or failure. Don't get too hung up on the word success or failure. Success could be something that could be a negative thing, right? Like a part not working. But anyways, again, the key thing there is that there's 2 options, right? Success or failure, whatever you happen to define those as. The probability of success is called P, and it's constant from trial to trial. And the probability of failure, we just denote it as Q, and it's 1 minus P, right? That's because every probability has to add up to 100%. So similar to if there's a 30% chance of rain today, then it follows that 1 minus 30 gives you the chance of not rain. So that's going to be constant trial to trial, and trials have to be independent. Remember, that means that the outcome of one trial isn't going to affect the outcome of the next. So think of flipping a coin. Whether you get tails does not affect whether or not you're going to get tails the next time, right? If X is the total number of successes in n trials of a binomial experiment, then X is called a binomial random variable. Whee! There we go. Having fun with my highlighter. So, the next slide, just bear with me. We'll get to the formula, I believe, in the slide after that. So this is not our final formula. I just would feel bad not showing this to you because a lot of textbooks show it to you this way. So here is the formula for probability of X in a binomial distribution. So for a binomial random variable X, the probability of X successes in n trials is given by this distribution. So this looks really scary, and you may or may not have seen this in math class. This is pronounced n factorial. And if you look on your calculator, you should have, if you have a scientific calculator, a button that maybe has the factorial symbol. So it's an exclamation mark. So it's not like I'm saying n, it's this is factorial. And what that means is if I write like 5 factorial, then that just means start on 5 and go down by integers and multiply all those numbers together. So it's a shorthand way of writing 5 times 4 times 3 times 2 times 1. You have a button on your calculator that does it for you. So this part of the formula we're going to simplify in a moment. I just wanted to show it to you in case you ever come across a textbook that has it like this. I don't want you to be sort of blindsided. Couple important points here, and we're not going to get into them. It's not the purpose of this course, but 0 factorial is equal to 1, which might be kind of strange, but there you have it. And it's not defined for negative numbers or fractions. So you can't do the factorial of like a half, nor can you do factorial of a negative number. Just doesn't work out. I'm going to talk about what these pieces are on the next slide here. So we're almost there. What does the equation mean? Well, the equation for a binomial distribution consists of the product. So product means multiplication. So there's the multiplication sign of 2 factors. This big ugly looking fraction with all these factorials, basically what this gives us, and again, we're not going to get into it. It's not a purpose of the course. We just end up using this fact that this gives us the number of ways to get x successes and n minus x failures in n trials. So if I'm doing 10 trials and I'm curious about, well, what's the probability of getting exactly 5 successes? This formula here, when I plug in x equal 5 and n equal 10, is going to give me the number of ways I can get 5 successful trials. Okay, so it thinks of all the possible ways it can be done. Again, I know it's a little confusing, but we're just going to roll with it, and I'm going to show you how you can do this on your calculator in an easy way in a moment. This part of the formula is actually the chance of getting x successes. So that would be, here it is, so probability of success right here, raised to the power of x, times probability of failure raised to the power of n minus x. So this would be the number of failures, right? X is the number of successes, and then P is, the probability of success. And then Q is the probability of failure. So that usually makes a bit more sense to people. I'm sorry, I spelled failure completely wrong. But anyways, that usually makes a bit more sense to people. And now, finally, here's the formula that we're actually going to use. So the good news is, yeah, there is a shortcut to the formula. And you're using this button, NCX, on your calculator. And what this is replacing is it's replacing this whole massive fraction. So instead of having to calculate this, there's a handy button on your calculator. It will literally look like this. So it'll be a button, and it's going to have a little subscript N, a little subscript X, and then the big C. Okay, so that is going to be the button that tells you the total number of ways you can do something in a certain way. You just have to plug in n, which is the total number of trials. So if I say I'm doing this experiment 100 times, n would be 100, and x is the total number of successes. So if I'm saying I'm looking for 20 successes, then you'd plug in 20 here. If you need help using this button, we can talk about it on Zoom, but it is important to locate it on your calculator. Usually, most calculators, there's 2 or 3 different ways this button works, but usually you plug in n first, then you hit this button, and then you plug in x, and then you hit equals, and it'll calculate it for you, and it's going to give you a number. As I said before, p is the probability of success, and 1 minus p, sometimes denoted as q, is the probability of failure. So, again, and I'll also show you, it's on your formula sheet, so it's right here, binomial probability distribution. So I got n, p, and 1 minus p. These formulas here we're actually going to go through in a moment. But right here, here's the formula we're looking at right now. So I have everything, x, p, n, and 1 minus p written out here. And I got the formula written out as well. This part is going to be next week or the week after. Can't remember. So there you have it. Okay. Let's try a question. And I know this is a lot, so it'll be important to get in as much of the homework as you can. So here's an example in voting that is going to be a binomial distribution problem. So in a recent Students' Council election, 19% of all eligible university students voted. If a random sample of 20 students were surveyed, find the probability that exactly half voted in the election. So one thing in this question is realizing it's a binomial distribution question. So the way I do it is I'm like, well, you either vote or you don't vote. So there's only really 2 outcomes to this. Okay, so what are the important numbers? Well, x is how many successes are we looking for? So if voting is a success, we're looking for exactly half of them voting in our sample. So our sample size was 20, so half of 20 is 10. Now, it says the probability of voting is 19%. Okay, so we're going to write p equals 0.19. Now you're going to notice I didn't write 19%. It's very important that you write everything as a decimal for this formula. It will not work if I plug in the number 19. You need to divide by 100 to get the decimal. Okay, now q, or 1 minus p, you can compute on your own. So I can go 1 minus 0.19, and that's going to give me 1 minus p. So this is basically the chance that you're not voting, right? If there's a 19% chance you're going to vote, then there is an 81% chance that you are not voting. There. So that's usually the first thing I do. Now, for the purposes of the example, I wrote the formula up here. So you would normally grab that from your formula sheet. And we are looking for the probability that x is equal to 10. And I'm not going to rewrite the formula because I have it up here at the top. So I'm going to start plugging in my numbers here. So for n, I'm going to plug in 20. And then write a big C. And then x is 10. Probability of success is 0.19 raised to the power of x, so raised to the power of 10 times 0.81 raised to the power of, what's n minus x? So I guess I'll just write it out, 20 minus 10. Perfect. Now, you're going to go to your calculator, and I suggest you take a moment here to try it out. So I'm going to write this first part of the formula. I like to break it up into chunks. So first I'm going to figure out what this is on my calculator. So like I said, every calculator is different. Usually write the 20, hit the button that says NCX, then type in 10 and hit equals. If that's not the case, you'll have to either check your manual or Google it or wait and talk to me on Zoom. I know every calculator in the world and I can figure yours out. So when you plug that in, if you did it correctly, you're going to get 184,756. So that's how many ways out of 20 people you can get exactly 10 of them voting. And I know that seems confusing, but it's like, say you got your 20 people lined up, or say you have 5 people lined up. Maybe this guy votes and then this guy doesn't and this guy doesn't, but then this guy does. So there's all these different arrangements for how 10 people out of 20 can vote. Okay, so and it's the order that you're asking them in. So maybe the first 10 people you ask voted and then the next 10 didn't. Or maybe it's the first person, right? There's all these different ways. And what this formula does is it figures out how many ways there are. And it turns out there's 184,000, okay? So I know that's hard to wrap your mind around, but thank goodness we have that formula, right? We can always do a smaller example where we could do the sample space like we were doing last week to help us kind of visualize it, but obviously this is a more complicated one. Right here, when you plug this in on your calculator, so I'm just going to be doing this next piece here, so 0.19 raised to the power of 10. Most of your calculators, you're looking for a button that looks like that, or it might be an x raised to the power of y button. Okay, so it means you're taking this number and multiplying it by itself 10 times. I get 0. Now, how many zeros do I have here? 2, 4, 6, 7. So 7 zeros. 1, 2, 3, 4, 5, 6, 7. That's a 0. That's a 0. 6, 1. Okay, that's a 0 right here. That's a 0. When you plug this in on your calculator, hopefully I don't run out of room here, but you're going to get 0.12158. There. Now you're multiplying these all together, so you can type them in on your calculator. You'll have this last one on your screen. So when you multiply them all together, you're going to get 0.00137 with some rounding. Or we might round it to 0.0014. Now the question doesn't really talk about what to round it to, so again, we'll talk about rounding later. That's not really our focus this week. So as long as you got the work and all that, you're good. Remember, this is as a decimal, so if you want it as a percentage, multiply it by 100. So when you multiply this by 100, you're going to get 0.14%. Okay, so when there's a 19% chance of people voting, 10 people voting is less than 1% chance, which seems reasonable. Okay, it is really important that you're going to do the homework question. So I'm showing you one question, and we're going to do some more cases in the following example. Very, very important that you do all the homework. I've literally went and chosen the questions you need from the book. Okay, so I'm not just throwing like, here's 50 questions. I'm like, here's like 5 questions that you need to do. Okay, do them as many times as you like. If you want to do other questions from the book, you can, but I'm basically suggesting to you the bare minimum that I think you need to do in order to succeed. Okay, trying to make your lives easier, you know. Okay, how do you deal with greater than or less than problems in the binomial formula? Okay, so in that last example, we calculated the probability that exactly 10 students voted. Well, what if I wanted to calculate the probability of less than 2 voting? So it's like, what? Well, probability that x is less than 2, what does that mean? Well, less than 2 people voting would mean 0 people vote, or 1 people vote out of the 20, right? So I would have to figure out the probability of 0 people voting and then add to it the probability that 1 person votes. So let's go ahead and compute that. Did you memorize your formula yet? Here it is. You know that you've done enough questions when you have the formula memorized. At least that's the case for me. You do have your formula sheet and you'll always have it. But if you know it by heart, then you have a good indication that you're on the right path. So let's plug in the numbers. This will give us 2 more kind of questions within a question that we can practice on. So remember, n is 20. We're just using the same data from over here, so maybe I'll just recopy it up here. So n is 20, x is whatever it is on the question that we're doing, and p was 0.19. 1 minus p was 0.81. Okay, so n is 20. And then write c, and then we're doing x is 0. And probability of p is 0.19. It's raised to the power of x, which is 0. And then 0.81. Now I'm going to do the next part in my head. So n minus x, 20 minus 0 is 20. Just to save myself some room. I'm going to do a no-no and just keep going on the same line and write equals. Remember, I prefer that you go to the line under it. So 20 C0 is 1. That makes sense, right? How many ways out of 20 people can you get exactly 0 of them voting? Right? There's only one way that can happen. Nobody votes. So that kind of makes sense. Anything raised to the power of 0 is 1. You can confirm on your calculator, but you'll get 1 for this bracket as well. Then this last bracket is going to give us something different. It's going to give us, when you type it in, I got 0.01478. Now, multiply it all together, and you get that the probability of 0 people voting is 0.01478. So underline that. Great. Now, let's do the probability of 1 person voting. So the only thing that's happening here is that x is equal to 1. All the other data in the question stays the same. So n is 20, you go 20C1, and then 0.19 raised to the power of 1, 0.81 raised to the power of, remember, n minus x, so 20 minus 1, that's 19. I like to save myself that work, and I just do it in my head. Now, when you type in 20C1 on your calculator, you can think about this. How many ways, if you have 20 people, could 1 person vote? Well, there's 20 ways that could happen. Right? So like the first person you ask voted, the following 19 don't. And then maybe in a different experiment, the first person didn't vote, the next person did, and the 18 after didn't, right? There's 20 ways that could happen. That's something that most of us could sort of visualize and make sense of. So I'm just trying to point that out to like kind of demystify like what this little piece of the formula is doing for us. Now, oops, I kind of made a mistake there. Let me get my eraser. All right, so 0.19 raised to the power of 1 is still going to just be 0.19. Now, when you go 0.81 raised to the power of 19, you're going to get 0.01825. All right, pat yourself on the back because you're just about there. Now, multiply that out on your calculator. So probability of exactly 1 person voting, you get 0.06934. Okay. So remember, why were we doing this? Well, we wanted to know the probability of less than 2 people voting. So probability of x being less than 2 was equal to the probability of 0 people voting plus the probability of 1 person voting. We have our 2 separate answers. When you add them up, what do you get? You get 0.08412, which is totally acceptable as an answer. I leave mine like that. If you like to write it as a percent, multiply it by 100, and you're going to get 8.412%. Yay! Give yourself a little smiley face. So there you go. That's one way of dealing with a greater than or less than problem. I'm not going to do a greater than problem. I think there's some in the homework, but you just need to figure out, well, what does it mean if less than 2 people vote? Figure out which cases it is, and then individually calculate them, add them up. Okay. Some of you might see an issue with this already. So I'm going to show you something called the complement rule. And the complement rule is not that you have to be nice to me. It's actually a mathematical principle. So let's use that last example again and just give you a different question and see what happens. So in that last example, if I asked what is the probability of 2 or more, say 2 or more students voting. Okay, so I'm saying, what is the probability that X is greater than or equal to 2? Now remember, we had 20 people surveyed. Okay, so for X greater than or equal to 2, if you use our last method, you're going to have to figure out the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5 plus all the ones in between till you get to the probability of 20. So I don't know how you feel about doing 18 calculations that look like this, but I think that's a nightmare. Okay, that's a lot of work. I'd never ask you to do that much work on a single question in a test. So you'll remember from the last week that all probabilities have to add up to 1. And we actually said there's something called the complement rule. Now, what's the complement rule? Well, if you want to know the probability of not A, then you go 1 minus the probability of A. So what does that mean for us in this question? Well, if we subtract all the cases that are not part of X greater than or equal to 2 from 1, then we'd be left with all the cases of 2 or more people voting, and that's what we want. Right now, look, this is way less work. What would it be to go 1 minus probability that X is less than 2? Well, probability that X is less than 2, that was our last problem that we just did. Less than 2 people voting means probability of 0 people voting and probability of 1 person voting. So if I just go 1 minus probability of 0 plus probability of 1, I'd be left with every other case, which would be 2 people voting and up. Do you see how that works? You might have to rewatch this slide a couple times, but that would be way less work, right? I only need to do 2 calculations versus 18, okay? So because we did this in the last example, we can just grab our answer from the last example and write it out. Go 1 minus 0.08412, and that is the probability that X is greater than or equal to 2. I'll write that again. And you get that the probability of 2 or more people voting is 0.9159, or 91.59%. Okay, couple things here to maybe talk about. Like I said, you might have to watch this slide a few times. I'm gonna just do a couple more, like not the actual work, but just doing the complement rule part of the problem. So let's see if I just said, okay, I want to know the probability that X is greater than or equal to 3. So 3 or more people voting, right? So this would mean you'd have to do probability of 3 plus probability of 4, dot, 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 until you got to probability of 20, right? So to use the complement rule, what would I have to do here? Well, the complement rule, I'm going to write probability that X is greater than or equal to 3. You start with 1 minus all the cases that are not in here. Okay, so what I like to do is I like to sort of write out for myself, well, what are the cases I need to do, right? So 3 to 20. What are the ones that are not in here? Okay, well, what's not in there? Probability of 0 people plus probability of 1 person plus probability of 2 people. So that's how I would use the complement rule in a very similar question. Are you guys starting to see how it works? Okay, you have to do a bit of thinking. It adds another step to the question. And thinking is hard, so yeah, these questions are a bit hard. What's your best defense against it? Doing some homework, okay? More practice, less problems. Does that make sense? Okay. This question here, I'm going to leave as an extra one. I have the solution on the next slide. The only thing is I was using the bogus formula. Instead of using NCX, I was using I wanted to show, someone asked one here like what it would look like, so I went ahead and did it. But you should be able to do it using the formula we have and get this answer. So you can pause, try it out. It is nice to try it out yourself. The next thing is just more for background. I grabbed these figures from your textbook. Like, what do binomial distributions look like when graphed? The reason I'm showing you this is because in the very near future, we're going to start looking at z-scores again. You guys will fondly remember z-scores and the normal distribution. The binomial distribution is like a very special case of a normal distribution, I guess. So you can see that as our sample size here gets bigger, so this is n equal 5, n equal 5, n equal 20. This is n equal 50 with p equal 0.5. You're starting to get this normal distribution popping out. Okay, we'll talk more about it when we actually get to that section. I'm just setting it up. So, here's some pretty pictures. And eventually we're going to be looking at stuff that looks like this. Like I said, you can do the binomial distribution using z-scores. And that's where we are headed. All right. We didn't look at mean and variance of a binomial random variable, so these formulas are straightforward. There are questions where we need to figure them out. So if x is a binomial random variable with those same parameters of n and p and q being 1 minus p, so basically a binomial distribution. If I ever ask you to calculate the mean of a binomial distribution, it's n times p. And that makes sense, right? P is the probability of success. So in our last example, it was 19% of people voting. And N is how many trials you're doing, right? So what would the average be? Well, it makes sense that it's the 20 people times the probability of success, right? So in this case, like approximately 4. Approximately 4, right? So that means that on average, 4 people would vote. So that kind of makes sense, but there it is. It is on the formula sheet, so I'll point it out. It's all these formulas up here. So here it is. It's called the expected value or mean, right? So I have both of them on there for you. What about the variance? A little bit less obvious, obviously, but here's the formula. So it's n times p times 1 minus p. And the standard deviation is just the same thing in the square root of it. So let's try a question, just so we can say that we did it. So what is it? TV failure. So X is the number of randomly selected televisions. The manufacturer claims the probability of not needing any repairs in the first 5 years is 90%. What is the expected number of televisions that would fail in a sample of 8 televisions? If you ever become an actuary, this is like day one. Like actuaries basically are the people who figure out warranty periods, right? So they do a bunch of testing and they're like, hey, most of your TVs don't fail for this long, so make the warranty period exactly 2 years. You ever notice that? Right? Like you have something, the warranty goes up, and like 3 days later something breaks. That's math at work, baby. So let's take a look here. N is 8. Whoopsie daisy. Sorry, my stylus has a clicky thing and I clicked it and I did not want. There we go. So N is 8. Yes, my battery is running low. N is 8. And P is, now, probability of success here, we didn't talk about it. So the probability of it not needing any repairs is 90%. So be careful, because it's asking what's the probability that it would fail. So our success is failure, right? So that's 10%, right? 90% work and 10% don't. So in this case, probability of success is not working. Okay, so don't get too attached to the word success here. I know that's confusing. When you do that, you get 0.8. So you're expecting approximately maybe 1 TV to fail. So 0.8 TVs, I should write. What's the standard deviation? Well, it's the square root of n, so 8, times probability of success, which is 0.1. 1 minus p is the probability of failure, 0.9. So when you do the square root of that, I just have the final answer, so type it in on your calculator, you'll get 0.85. So remember, standard deviation is the average difference from the mean of all the different data points, so it's about 0.85 TVs. So we'd expect approximately 1 TV to fail within the first 5 years out of that sample size. There you go. This is our last topic, and it is a small one, and the formula does look kind of weird. It is on your formula sheet, and it is a question that you can expect sometimes to pop up. So consider the number of times an event occurs over an interval of time or space. And really, that's going to be the big giveaway that it's a Poisson distribution, is that you're going to have some sort of time or space part of the question, like an average over time. So if the probability of the occurrence is the same for any intervals of equal length, and the occurrence in any interval is independent of an occurrence in any non-overlapping interval, and x is the number of occurrences in a specific interval, then x is something that we call a Poisson random variable. Now, it's named after the French mathematician who figured this out way back when, in case you just want to go and Google it. So let's think about maybe a more practical example of what this distribution looks like in real life. So let's say that you typically receive 5 unsolicited text messages from friends in a day. Okay? This kind of becomes your expectation. And of course, you're going to find that there's a spread, right? Some days you might get more than 5, some days less, and maybe some days you might not get any at all. But given that the average rate is 5 messages per day, and assuming that those 5 messages a day are totally random, like they're not being influenced by you posting something to Instagram, or there's some external factor that's causing them. It's just, on average, you get 5 text messages a day. then that's going to be a Poisson distribution. And if we use the formula for a Poisson distribution, what that formula is going to be able to tell us is how likely it is, so again, this is probability, that you might get 6, 7, or any other text messages in a day. So the Poisson distribution basically predicts the degree of spread or variation around a known average rate of occurrence over a given time frame. So like I said, you sort of have this giveaway that it's a Poisson distribution, because it's going to be talking about a time frame. 5 messages per day. And what we're going to be able to use a distribution for is to sort of predict what kind of variation can you expect over that time frame for whatever variable we're looking at. Here's a picture of a Poisson distribution in practice. Now, in this case, I think M is like the sample size. I just want to point out that Poisson distributions are probabilities where the occurrence is typically small. It's actually called the law of small numbers. If you go Google that, you'll find some stuff. Actuaries, which work in the business world, are usually interested in these sorts of things. Actuaries usually come up with like, how much should the insurance premium be for this thing or that thing. Large catastrophes don't often occur very frequently, so some of them follow Poisson distributions. Well, as the sample, as it gets larger and larger here in our picture, if you're looking at these diagrams of the distribution, once we get to 8, this is already looking like a normal distribution. So it doesn't take long before a Poisson distribution is going to start looking like a normal distribution, and then we'd use a different formula. So, what is the actual formula? Well, if mu is the mean or the expected number of occurrences during a specified interval, the probability of x occurrences in the interval when mu are expected is described by this formula here. Okay, now this is a lot of stuff going on here. This here is not a variable. It's actually a special number called Euler's number, or the natural logarithm. So it's a stand-in for the number 2.71828. Now, purposes of this course isn't to explain that number. It's a number that comes up a lot for logs and things like that. You're just going to have to know that this is a number that pops up in this formula. There is a button on your calculator for this number, so you'll see something like that on your calculator. It might be a second function. Again, if you bring your calculator, if you take a good look at it, you can find it, and if you need my help, I can certainly show you where it is. It's only on scientific calculators generally, so that's another thing to consider. So in this formula, x is going to be can be any of the values 1, 2, 3, 4, 5. So it's going to be the number of occurrences you're usually looking for. The exclamation mark, remember, is factorial. So again, that's another button on your calculator, and we saw it when we did the binomial distribution. And then mu is the average. Okay, so let's look at an actual question. So an air traffic control center has been averaging 20.8 errors per year. And lately they've been making 3 errors per week. So kind of like a bad, if you're only getting 20.8 errors per year and you're doing 3 errors in a week, that's not good. So this is a Poisson distribution because you got an average over a time frame, so it's per year. So let x be the number of errors made by the ATC center during 1 week. Given that you have this average here, so mu is 20.8, and there's 52 weeks per year, then you're going to take the 20.8 and you're going to divide by 52, and you have your average errors per week. So this is what we're going to use in this question because they're asking for a week. So find the probability that 3 errors will occur in a week. And over here, I threw the formula down again, just so you can have it. And we're basically looking for x equal 3 when mu equals 0.4. Now, I'll give you a moment to try to pop it in the formula on your own. So I suggest you pause the video here. And, whoops, my bad. I lost me. There we go. So you're going to write something like this. Now, remember, E is just the number 2.71, so we're just going to write the symbol for it. And we write it to the power of the negative mean times the mean, which is 0.4, raised to the power of x. Now, x is 3, so you're going to raise to the power of 3. Then we're going to divide by x factorial, so 3 factorial. Now, you can pop that in on your calculator. Give you a moment. You might want to pause the video. But the answer I get is this one right here. And again, it doesn't really say anything about rounding, so we'll just keep a couple decimals there. Find the probability that no errors will occur in a week. So basically, very, very similar question. I can show you the work for it. So it's going to be the same formula as before. Our mean hasn't changed, so still e to the power of negative 0.4. And then 0.4 raised to the power of x, which is 0. And then divided by 0 factorial. Just remember, this is not the same thing as 0. This is 0 factorial, which is equal to 1. So when you pop this in on your calculator, you're going to get 0.6703. So the probability that there's going to be no errors in a given week is going to be about 67%. All right, just multiply by 100 to get the percentage. So what I guess I'm trying to show you is that these questions aren't horribly difficult, right? Like you're plugging into this weird looking formula and you're going to do it on your calculator. The tricky part is realizing when you have a Poisson distribution. So watch out for an average over time, and that's usually an indication that you have a Poisson distribution, and you're also expecting fairly small numbers as well, as far as like, you know, in this case, we're not talking about, you know, the average wasn't like, 900 errors per year. It's a very, very small number. So remember, as these things get bigger, they start looking like normal distributions, and it's less likely it's going to be a Poisson question. I just threw this in here because some textbooks use these probability tables. We're not going to do this, but there are probability tables that allow you to quickly look up Poisson distributions. Where they sort of pre-calculated with a pre-calculated mean and a number of occurrences. So they've kind of pre-calculated some values for you. I just thought I'd show it to you, but I don't plan on using it. Couple things about mean and variance of a Poisson variable. So if x is a Poisson random variable with the parameter mu, then the mean is merely going to be the mean, and the variance is going to be the mean as well. So that's a little different. Okay, so the variance is indeed the mean. And this is on our formula sheet, so don't worry too much about memorizing everything. Okay, but the variance is the mean. So then this standard deviation is just going to be the mean, the square root of the mean. A couple more pictures of Poisson distributions. So you can take a look. If you can imagine like a trend line, like connecting like the corners of these, you can see this is very similar to that first picture that I had. And then with a mean of 0.5 looking like this, mean close to 2, mean close to 5. As that mean gets bigger, this starts to look more and more like a normal distribution, right? This one here is looking like it's skewed over here on the right-hand side. So there you have it. Just trying to reinforce that concept that as the mean gets bigger, looks more and more like a normal distribution. Okay, so let's go back to that last example and just very quickly calculate the mean and the standard deviation. So same exact numbers, 20.8 errors occurred in the average year, and we're assuming that x is the number of errors during a week. Okay, so we divide the 20.8 by 52, and we get our mean of 0.4 errors per week. And because the standard deviation is equal to the square root of the mean, you plug in 0.4, do the square root of it, and you're going to get your standard deviation. So I could ask you a question like that. Well, there you have it. We made it to the end of this chapter. Super important that you try out the homework, the guided examples, all those things. Just remember, doing it once is not necessarily enough, and doing it while you're staring at the answer key also is not enough. It's a starting point, but you really need to get to the point where you can do these questions without really looking. The summary, I'll leave it for you to read over. The biggest, I'm saying a lot, it's driving me mental. The biggest thing definitely in these notes this week, something that will be coming back, is definitely the binomial distribution. Okay, so like I said, Poisson distributions is this itty-bitty thing that we do. We don't go very deep into it. So what we covered today is basically as far as we get. Check the homework for a question on this. Definitely get familiar with the binomial distribution. Today we did the discrete version of it. In the future, we'll be looking at what happens when a binomial distribution is continuous. And that's going to bring in Z-scores. So, We will see you next time. Bye-bye.